Hello, in this video I'm going to show you how to use the second derivative to examine concavity and any potential inflection points for the function. First of all, the second derivative is just the derivative of the first derivative. Hence the clever name, the second derivative. Okay. Let's talk about concavity for a second. Concavity examines how functions increase or decrease. Increasing or decreasing is determined by the derivative. How they increase or decrease is determined by the second derivative. We call that concavity. So consider two ways a function could increase. And on the black interval, that's one way a function could increase. And on the blue interval is a second way a function could increase. The black interval we call concave down. It's concave down because the rate at which it's increasing is decreasing. The tangent line here is steeper than the slope of the tangent line here. Okay. Up here, the function is concave up, still increasing, but now it's increasing at an increasing rate. We have a pretty shallow slope of the tangent line here, a pretty steep slope of the tangent line here. So our second derivative is what tells us about concavity. So here's the theory. Whenever the second derivative is positive, y will be concave up. And it will look like part or all of that upwards U shape. Okay, what that means is that the function's either increasing or decreasing, but the rate at which it's doing so is increasing, much like this blue piece over here. When the second derivative is negative, the function y is concave down, much like the black stretch over here, meaning that whether it's increasing or decreasing the function, the rate at which it's doing so is decreasing, and that looks like part or all of an upside down u. Okay. Furthermore, when the second derivative equals 0, y might have what we call an inflection point. An inflection point is a change of concavity. Okay? So that's the theory, much like we analyze the first derivative for its sign, positive, negative, and how the sign of the first derivative has meaning, gives us increasing and decreasing intervals for the function. And the zeros of the first derivative gives us critical points. The second derivative also tells us information, but it pertains to concavity and potential inflection points. So let's take a look at a specific example. Here's a quartic, and we're going to discuss the concavity and the inflection points for this function. So I'm going to begin by, first of all, kind of making some guesses. It looks like we have a concave up piece here. We have a concave down piece right about there. And we have another concave up piece for the rest of the function. So it looks like my conjecture is that we have two inflection points here and about there. And I'm going to use the calculus to verify that. So I'm going to find the second derivative, and first I'm going to find the first derivative. And then I find my second derivative, which is the derivative of that. Which when I factor out a 12x, a little bit easier to deal with. Okay, now again, I'm going to look for the zeros of the second derivative, potential inflection points, and just like I do with my first derivative, the zeros of the second derivative are going to be the pillars of my little chart. And this chart, however, is going to use the second derivative instead of the first. So I'm going to structure this chart about the zeros of the second derivative, and those are, for now, potential inflection points, IPs. Now what I'm going to do is graph the second derivative, because I need to know the signs of the second derivative. It is a parabola. It opens upwards. Here are the two zeros. So I know that my second derivative looks something like that. And that's enough for me to know. So I'm going to look to the left of 0. And that gives me this piece. And there's positive second derivative. It's above the x-axis, which means over that interval, y, the function, is concave up. And I'll just note it like that, concave up. I'm going to look between 0 and 2, which is this piece right here. And note that over that interval, my second derivative is negative, which means over that interval, y, my original function, x to the fourth minus x cubed, is concave down. So what I've just verified is that indeed, when x equals 0, my function has a change of concavity. It changes from concave up to concave down when x equals 0. Concave up, concave down. Here's your inflection point, 0. And that's 0, 0, obviously. Okay. Now I'm going to look to the right of 2. On my second derivative, note again it's above the x-axis. Positive land, which means once again my function over that interval will be concave up, which therefore verifies another change in concavity, down to up. Change in sign of the derivative, second derivative, negative, positive. So 2 is my second inflection point. When I plug 2 into the function, the y value is 16 minus another, oh, there should be a 4 there, sorry. Sorry for that error. That's a 4 there, there's a 4 there. So my y value really is negative 16. Okay, so to summarize, I have 2 inflection points, changes of concavities, and that's 0, 0, and 2, 16, negative 16. Concave up over the red intervals, so that's when x is less than 0 and greater than 2. And I have concave down for x on the blue interval is between 0 and 2. Thanks for listening. Have a great day.